Okay, so we were talking about liquids, and we saw that the pressure at any depth equals the pressure at the surface plus the density of the fluid times G times the depth. So the pressure is linearly related to the depth. That's important. Now we want to talk about gases. All right, so here's the question, so get ready, pause your video, get ready to vote. All right, what is the primary cause of pressure in a lab-sized container of gas? A little beaker. Now we haven't talked about this, so I just want you to guess. Well, the answer is 3, molecular collisions. All right, molecular collisions. We talk about atmospheric pressure a lot. You know, we're going to use that in this equation if the beaker is open to the atmosphere, right? So there's lots of units for atmospheric pressure. So people talk about 1 atmosphere. So that's a unit. It's not a metric system unit, but it's a unit that people use for atmospheric pressure. So 1 atmosphere equals 101.3 kilopascals. I just remembered, I forgot to say something. Pressure is force divided by area, right? Perpendicular force divided by area. Let's look at the units. What's the unit of force? Newtons. What's the unit of area? You know, meters squared. Well, you know how in physics we have all these units named after people. This is called a Pascal. Named after Mr. Pascal, of course, all right? So this is the correct metric system unit for pressure, pascals. Okay, so atmospheric pressure is a 101.3 kilopascals. And another unit you'll see sometimes, especially in the United States, is PSI. So that's equal to 14.7 PSI. What's a PSI? PSI is a pound per inch squared. So, you know, look at your bicycle tire or something like that. It'll probably have PSI. You know, that's very common in the United States. But again, the metric system is Pascal, right? Now, in your equations for P0, when you have atmospheric pressure, don't bother with this. Just say 10 to the 5th pascals. Close enough, right? I mean, 101.3 times 10 to the 3rd, that's basically 10 to the 5th. So I'm always going to just say that atmospheric pressure is 10 to the 5th pascals. And again, don't forget, you know, pressure is force over area. So force is pressure times area. Any direction, right? Any direction, okay? All right. Here's a picture of a vacuum cleaner. How does a vacuum cleaner work? Is the dirt sucked into this tube? Are there these arms that come out and suck up the dirt in the tube? So think about it. Just pause your video and think about it. Now I'm going to give you a hint, and we'll talk more about this later, but I want to give you a hint. Think of the name of this thing, vacuum cleaner, right? Vacuum cleaner, right? So you have propellers, you know? And so you have propellers, and what do? You know, attached to a motor, right? They create a partial vacuum, all right? A partial vacuum in the tube. So think about it. What we're going to learn later, so you have a propeller creating a partial vacuum in the tube. We're going to learn later that that decreases the pressure. So we have a small amount of pressure in the tube, but we have the regular atmospheric outside the tube. So think about it. If we have, you know, 10 to the 5th pascals outside the tube, and then we have less, considerably less pressure in the tube, what happens to the dirt? The atmospheric pressure is pushing the dirt into the tube, all right? So that's basically how a vacuum cleaner works. It establishes a partial vacuum here, and so the pressure it decreases here. So the vacuum cleaner, you know, you have a brush, you know, it kicks up the dirt. So the atmospheric pressure shoves that dirt into the tube. Okay? Pretty cool. Can you see this? Okay. Okay. Look at what's this thing called? It's called a suction cup. Why was it so difficult for me to pick up the suction cup? Well, there's no air underneath the suction cup, right? There's no air underneath it, so all we have is the atmospheric pressure pushing down on it. So that's why, okay. Anybody have kids here? This is a great invention. You know how little kids, when they're learning how to eat, they push everything on the floor. If you don't know that, you will. And so this is a dish attached to a suction cup. And so that plate remains stationary. I mean, of course, they're still going to take the food and another dish and throw it on the floor. But anyway, this helps. Okay, this helps. Let's see. I put my finger here. How come I can lift it up? I mean, how come this is really difficult to lift up, right? But yet it's really easy to lift up my finger. Why? So think about it. Well, the reason is because, I have fingerprints and all that, right? This is not a suction. And so there's air above and below my finger. And so what's the net force on my finger? 0. Okay, so it's easy. All right. Okay, moving along. So everybody read that, please, and vote. So pause your video. And just guess. We haven't talked about it yet, so just do your best. All right, so we have a closed container of water. I don't care how large it is. It could be really, really large. Suppose this P0 is increased by a piston on the top. So we're going to push down on this thing, a piston. Okay? So the P0 is increased by a small piston on the top of the container. How is this increase in pressure transmitted to the water? Well, it turns out that the increase in pressure occurs everywhere in the water. And that's called Pascal's principle. And you read that and you say, whoopee, what do I care? What good is that? Well, I'm sure you've learned by now that a lot of people become famous because they learn how to apply the laws of physics to solve practical problems. All right, so let's do it. Let's see how this is important. All right, so here's this big container. And it's filled with some kind of a liquid, hydraulic fluid, but we don't care about that right now. And this is open, and this is open. And here's a piston, right? So here's a little piston, and somebody's applying a little force here, And here's a car, right? So there's a force there. And what did we learn about containers like this? Draw a horizontal line, same pressure. Agree? Let's read this. So pressure P1 is due to atmospheric pressure pushing down plus the pressure, this force divided by this area. Okay. Pressure here is also due to atmospheric pressure. It's also due to this F2 divided by this area A2, but it's also due to this rho GH, right? Rho GH? Or rho GD, whatever you want to call it. So yeah, sometimes I use H, sometimes I use D, sorry. Okay? So this has this additional term, rho GH. Whatever. Okay? Now, so let's write the equation. So on the left, we have P atmosphere plus F1 over A1. On the right, we have atmosphere plus F2 over A2. We also have rho G, I'll use H to correspond with a picture. Now, what we want to do is we want to make this small compared to this. Well, first of all, this cancels, right? So this cancels. So we want to make this term small compared to this and to this. And it's really easy. I mean, all you have to do is make H kind of small, you know? And you just want to use, you don't want to use water, you want to use something that has a really low density. So all I'm saying is easy to make this small compared to this and this. So let's do that. So if it's small, we could ignore it. So goodbye. All right, so what are we left with? What we're left with is F1 over A1 equals F2 over A2, right? Which means that F2 equals A2 over A1 times F1. Okay, now look at that. So let's say that A1 is really, really small, you know, the cross-sectional area here. Let's say that A2 is really, really large, the cross-sectional area here. So so A2 over A1 is going to be a very, very large number. So that means that if this is a really, really large number, F1 doesn't have to be very big at all to have a huge F2. Agree? And so this is how you pick up a car, right? You make this ratio really, really large, and then this doesn't have to be so big, but just like an ordinary F1 times a huge ratio here means you can have a huge F2 so you can pick up a car. So that's called the hydraulic jack. And they're used everywhere, you know, all over the place, okay? So a very, very small F1 can lift up a car. All right. So there it is, okay? So F2 equals F1 times this ratio. Okay, so yeah. With construction equipment, you know, they're able to move these incredibly massive amounts of dirt and rocks and things like that. Well, they use hydraulics. They use hydraulics, so they use this principle. Okay, here. This is an 8-ton hydraulic jack. Just this little thing, you know. It can lift 8 tons. So 8 tons is 16,000 pounds. So an average car weighs 4,000 pounds, let's say. So amazing, right? Because it uses the principle of hydraulics. Okay, here's a true story. So before we moved to Hawaii, we lived in Illinois. We had brought this great and beautiful, nice house. Only problem is it had a problem with the sidewalk, right? So here's the house, concrete. So this slab somehow, I don't know, anyway, it was like that. And we had little kids at the time, so what do little kids do? You know, they walk along the sidewalk and don't pay attention and they trip, right? And so, of course, we had to, we thought, oh, we got to fix this thing. So at first, you know, I thought, well, you know, well, first of all, we called some companies to see how much it would cost just to move this, you know, this piece of cement or concrete, whatever. It was like, you know, like that, right? So we figured that can't cost that much just to pick it up. So the quotes that we had were like $1,000. Well, we had just bought a house, so we didn't have an extra $1,000, you know? So we didn't do that. So then I thought, well, you know, let's try levers. So we had these really, really long, couple long boards. So we set up a lever, and I said, come on, I got my wife to help. You know, so we jumped on them, you know, figuring if the board was long enough, it would pick it up. Well, it didn't work. The boards broke. So then I thought, okay, come on, you're a physicist. Use your brains. So then I remembered that we had 2 hydraulic jacks in the garage. So what I did, I dug a hole. So I had a nice surface. Then I put bricks on the surface so it was really sturdy. Then I put the hydraulic jacks right here. And come on, they can pick up a car. And I had 2 of them. So I just put the hydraulic jacks there and just do, and the cement just went, so it was perfect. So there you go, we learned something useful today. All right, let's see, let's go back to this. So one of the assumptions that we're going to say is for a liquid, we're going to say a liquid is incompressible. So the volume doesn't ever change under normal circumstances. This is just for a liquid. So because a fluid, a liquid, is incompressible, this volume has to equal this volume. Well, what's the volume here? It's the cross-sectional area times the depth. And here's the cross-sectional area times the depth. All right? So we'll use that once in a while, that the volume here equals the volume there. All right, here's a question for you. So pause and think about it. Okay. So let's do it. On the right, the force is 10,000 newtons. The area is 10,000 millimeters squared. Now look, here the unit is millimeters squared also. So we don't have to convert to meters squared. It's a total waste of time. So here, what's the ratio? Remember, how did I come up with this? I came up with this because we said that F1 over A1 equals F2 over A2, correct? So what's this ratio? What's the pressure? What's the pressure here? It's the force divided by the area. Now in these units, that's given, the ratio is 1. So therefore, what has to be the ratio here, the pressure here? It has to be 1. So if this is 10 millimeters squared, what does the force have to be? 10 newtons. Now, you should be incredibly impressed because, I mean, come on, this is a car. What's 10 newtons? It's basically if you put a 1 kilogram mass, 1 kilogram times g, 9.8 meters per second squared, is 9.8 newtons. That's 10 newtons basically, right? So all I'm saying is if you just put a 1 kilogram mass on this piston, you can lift a car. So that's incredible, right? That's incredible. That's the power of hydraulics. All right, here's a new subject. So everybody think about that and get ready to vote. Okay, if the air pressure in a tire equals atmospheric pressure, what is the condition of the tire? What do you think? That's flat, right? It's flat. And so what you need to know is this. So absolute pressure equals atmospheric pressure plus gauge pressure. So when you're doing a homework problem and they're talking about pressure, you have to understand, are they asking for absolute pressure or gauge pressure? Right? You have to know that because they're not exactly the same, right? All right, let's see. What we're going to do now is we're going to do a homework problem. So this is right out of the book, so everybody read that, please. Let's talk about it right now. All right, so here we have this weird setup. So this is a right circular cylinder. These are all right circular cylinders, okay? And there's oil inside. This is not open. This is closed, obviously, right? This is closed. And this is open, but there's a piston on it, 10 kilogram piston floating, okay? So how much force does the fluid exert on the end of the cylinder here? How much force does the fluid exert on the end of the cylinder here? So what's the concept? Well, I mean, you know, here you have different depths, agree? And the question is asking force, but wait a minute, we're talking about pressure. But come on, pressure is force divided by area, right? So if we know the pressure, we can figure out the force. So that's the equation. Oops. That's what we want to deal with. Pressure equals P0 plus rho g depth. All right, let's do it. Okay, so there's our equation, right? Okay, so here's the thing. All right, so let's start off. What's P0? Well, here's P0, right? So there's atmospheric pressure, plus there's the pressure from this piston. So we've got to figure that out. So P0. So P0 is atmospheric plus the pressure from the piston. Okay. Atmospheric is 10 to the 5th pascals. Now, what's the pressure exerted by the piston? Well, again, pressure is force over area, right? And so what's the force? Well, this is the mass, so the force is just mg, the weight, right? So the pressure of the piston is the force, which is mg, 10 kilograms times 9.8 meters per second squared, right? That's the weight, that's the force of gravity. Then we have to divide it by the cross-sectional area. Well, this is a cylindrical tube, right? So it's going to be pi r squared. So pi times r squared. Now you got to convert, obviously, right? You know. Okay, I promise you when you do that, you get 1.78 times 10 to the 5th pascals. Okay, so that's P0. Now, so we have P0, but we want to know the pressure, you know. So for A here, what is the depth? That's the important question, right? I mean, that's the whole question. So what's the depth? Well, this is 100. This is 60, so we're assuming this is 30, this is 30. So if this is 100 and this is 30, what's that depth right here? It's 70, right? 100 minus 30 is 70, right? Draw a horizontal line here, draw a horizontal line here. This is the depth, so it's 70 centimeters, okay? So the depth, so at A, the depth is 70 centimeters. Oops, 0.7 meters, all right? Okay, so therefore, we have to figure out rho GD. So rho GD, okay, rho is the density of oil, 990 kilograms per cubic meter. G, 9.8 meters per second squared. The depth, 0.7 meters. I promise you, when you do that, you get 6,174 pascals. So therefore the density, the pressure at A equals this plus this. And I promise you that's 1.84 times 10 to the 5th pascals. Okay? But that's not what they're asking. They want to know the force, right? Well, again, pressure is force over area. So therefore, the force at A equals the pressure at A times the cross-sectional area. Right? At A, right? At A. So that's 1.84 times 10 to the 5th pascals. And then that's the area's cross-sectional. So it's pi. And then the radius of that thing, A, is 0.1 meter squared, right? And so you work all that out, and you get 5786 newtons. There you go. So that's the answer for part A. For part B, what's the only difference for part B? P0 is the same, right? But what's the depth at B? Well, here's 100 centimeters. Here's 30 centimeters. So it's 130 centimeters, okay? So basically, all you have to do is just use the depth, 130 centimeters, 1.3 meters, and then you just work it out. Make sure you do this. Make sure you understand this problem. you know, there's not many equations in this chapter for fluids at rest. That's one of them. And so this is going to be what you're going to see on your homework, and that's what you're going to see on your exam. So please make sure you understand this problem. That is enough for today. Thank you very much.